In the rapidly evolving landscape of modern computing, artificial intelligence, AI, has emerged as a transformative force, reshaping industries and redefining the boundaries of what machines can accomplish. At the heart of this revolution lies a critical technological enabler, AI chips. These specialized hardware components, designed to accelerate machine learning and deep learning workloads, have become indispensable in the quest for faster, more efficient, and more intelligent computational systems. The significance of AI chips extends far beyond mere performance gains. They are foundational to the realization of new applications, the democratization of AI capabilities, and the sustainability of the digital future. To appreciate the importance of AI chips, it is essential to understand the unique computational demands posed by AI workloads. Traditional central processing units, CPUs, which have powered computers for decades, are optimized for general-purpose tasks and sequential processing. However, the algorithms that underpin AI, particularly those involving deep neural networks, require massive parallelism and the ability to process vast amounts of data simultaneously. Training a state-of-the-art deep learning model can involve billions of parameters and trillions of operations, making it impractical for CPUs alone to handle such tasks efficiently. This gap between the requirements of AI workloads and the capabilities of conventional processors sparked the development of specialized AI chips. Graphics processing units, GPUs, were among the first to be repurposed for AI tasks due to their inherent parallel architecture, which was originally designed for rendering graphics, but proved well-suited for matrix multiplications and other operations common in neural networks. The adoption of GPUs for AI marked a pivotal moment, enabling breakthroughs in image recognition, natural language processing, and other domains. Yet, as AI models grew in complexity and scale, even GPUs began to encounter limitations in terms of power consumption, latency, and scalability. This led to the emergence of dedicated AI accelerators, such as tensor processing units, TPUs, field programmable gate arrays, FPGAs, application-specific integrated circuits, ASICs, and neuromorphic chips, each tailored to specific aspects of AI computation. The evolution of AI chips reflects a broader trend towards hardware-software co-design, where advancements in silicon architecture are closely coupled with innovations in AI algorithms. This synergy has yielded remarkable benefits. For instance, AI chips can be optimized for low-precision arithmetic, exploiting the tolerance of many deep learning models to reduce numerical accuracy, which in turn leads to significant gains in speed and energy efficiency. Similarly, the integration of on-chip memory and high-bandwidth interconnects minimizes data movement, a major bottleneck in traditional systems, thereby accelerating both training and inference phases of AI deployment. These enhancements not only enable researchers to experiment with larger and more sophisticated models, but also make it feasible to deploy AI at the edge, powering intelligent devices from smartphones to autonomous vehicles. The proliferation of AI chips has had a profound impact across diverse sectors. In healthcare, for example, AI-powered diagnostic tools rely on rapid image analysis and pattern recognition, tasks that are accelerated by specialized hardware. In finance, real-time fraud detection and algorithmic trading systems leverage AI chips to process vast streams of data with minimal latency. The automotive industry depends on AI chips for advanced driver assistance systems, ADAS, and self-driving technologies, where split-second decision-making can mean the difference between safety and disaster. Even entertainment and creative industries benefit, as AI chips enable real-time video processing, content generation, and immersive virtual experiences. One of the most compelling advantages of AI chips is their role in democratizing access to artificial intelligence. By lowering the computational barriers to entry, these chips empower startups, researchers, and organizations of all sizes to harness the power of AI without the need for massive data centers or exorbitant energy budgets. Cloud service providers now offer AI-optimized instances, allowing users to rent access to cutting-edge hardware on demand. Meanwhile, edge AI chips bring intelligence closer to the source of data, enabling privacy-preserving, low-latency applications in areas with limited connectivity. This widespread availability of AI hardware accelerates innovation and fosters a more inclusive ecosystem, where the benefits of AI can reach a broader spectrum of society. However, the growing reliance on AI chips also raises important challenges and considerations. As the demand for AI computation skyrockets, so too does the energy consumption associated with training and running large models. Data centers equipped with thousands of AI accelerators can consume megawatts of power, contributing to environmental concerns and operational costs. To address this, chip designers are exploring novel architectures and materials, such as 3D stacking, photonic computing, and quantum-inspired designs, aimed at achieving greater efficiency and sustainability. Moreover, the push for edge AI necessitates chips that can deliver high performance within stringent power and thermal envelopes, prompting innovations in low-power design and heterogeneous integration. The global race to develop advanced AI chips has also taken on geopolitical significance. Looking ahead, the trajectory of AI chip development promises to unlock new frontiers in computing. As models continue to scale, with trillions of parameters and unprecedented complexity, the need for ever more capable hardware becomes acute. Innovations such as chiplet architectures, where modular components can be assembled to create customized accelerators, offer flexibility and scalability. The convergence of AI with other emerging technologies, such as 5G, the Internet of Things, IoT, and quantum computing, will place new demands on AI chips to support heterogeneous and distributed workloads. Furthermore, the integration of AI chips into everyday objects, from wearable devices to smart appliances, heralds an era of ubiquitous intelligence, where computation is seamlessly woven into the fabric of daily life. The societal implications of AI chips are equally profound. By enabling machines to perceive, reason, and act autonomously, these chips catalyze shifts in labor markets, education, and human-machine interaction. They facilitate the automation of routine tasks, freeing humans to focus on higher-order creativity and problem-solving. At the same time, they raise ethical questions about accountability, transparency, and the potential for bias in AI-driven decisions. The design of AI chips must therefore be guided not only by technical considerations, but also by principles of fairness, inclusivity, and societal well-being. In the realm of scientific discovery, AI chips are accelerating progress in fields ranging from genomics to climate modeling. By providing the computational horsepower needed to analyze complex datasets and simulate intricate systems, they enable researchers to uncover patterns and insights that would be otherwise inaccessible. The iterative feedback loop between AI-driven hypothesis generation and experimental validation is shortening the path from discovery to application, driving innovation at an unprecedented pace. Education and workforce development are also being transformed by the advent of AI chips. As AI becomes a core competency across disciplines, there is a growing need for curricula that integrate both software and hardware perspectives. Understanding the capabilities and limitations of AI chips empowers students and professionals to design more efficient algorithms, optimize resource utilization, and anticipate future trends. This interdisciplinary approach fosters a new generation of innovators who can bridge the gap between abstract theory and practical implementation. The open source movement has played a pivotal role in advancing AI chip technology. Initiatives such as RISC-V and OpenAI hardware have lowered the barriers to entry for hardware design, encouraging collaboration and knowledge sharing across academia, industry, and hobbyist communities. This democratization of hardware innovation mirrors the earlier open-source software revolution, enabling rapid prototyping, customization, and experimentation. At the same time, it poses questions about intellectual property, standardization, and the balance between openness and commercial viability. From a business perspective, the rise of AI chips is reshaping competitive dynamics in the technology sector. Companies that once relied solely on software differentiation are now investing heavily in custom silicon to gain a performance edge. The likes of Google, Apple, Amazon, and Tesla have developed in-house AI chips tailored to their specific workloads and use cases, reducing dependence on third-party suppliers and optimizing for unique requirements. This vertical integration enhances control over the end-to-end user experience, but also raises the stakes in terms of research and development investment, talent acquisition, and supply chain management. Interoperability and standardization remain ongoing challenges as the ecosystem of AI chips diversifies. Ensuring that different hardware platforms can seamlessly run the same models and frameworks requires concerted efforts in software abstraction, compiler development, and benchmarking. Industry consortia and standards bodies are working to establish common interfaces and performance metrics, fostering a more cohesive and interoperable environment. This in turn lowers the barriers for developers and accelerates the adoption of AI across sectors. The importance of AI chips is further underscored by their role in enabling real-time, mission-critical applications. In fields such as robotics, aerospace, and defense, the ability to process sensor data and make split-second decisions is non-negotiable. AI chips provide the deterministic performance and reliability required for such scenarios, often under harsh environmental conditions. Their robustness and adaptability are key factors in the successful deployment of autonomous systems in unpredictable and dynamic settings. The integration of AI chips with cloud infrastructure has created a virtuous cycle of innovation. On one hand, cloud providers leverage economies of scale to deploy massive fleets of AI accelerators, offering customers elastic access to high-performance computing resources. On the other hand, the feedback from diverse workloads informs the design of next-generation chips, leading to continuous improvements in efficiency, scalability, and cost-effectiveness. This symbiotic relationship between hardware and cloud services is accelerating the pace of AI adoption and expanding the range of feasible applications. Edge computing represents another frontier where AI chips are making a decisive impact. By bringing intelligence closer to where data is generated, edge AI chips enable real-time analytics, reduce latency, and alleviate bandwidth constraints. This is particularly valuable in applications such as industrial automation, smart cities, and remote monitoring, where connectivity may be intermittent or data privacy is paramount. The miniaturization and ruggedization of AI chips are opening up new possibilities for deployment in challenging environments, from offshore oil rigs to agricultural fields. In the context of personal computing, AI chips are redefining the capabilities of consumer devices. Smartphones equipped with neural processing units, NPUs, can perform advanced image enhancement, voice recognition, and augmented reality tasks locally, without relying on cloud connectivity. Laptops and tablets leverage AI chips for features such as background noise cancellation, adaptive battery management, and personalized recommendations. These enhancements not only improve user experience but also set new expectations for device intelligence and responsiveness. The interplay between AI chips and other emerging technologies is fostering a wave of cross-disciplinary innovation. For example, the combination of AI chips with blockchain enables secure, decentralized decision-making in applications such as supply chain management and digital identity verification. In the realm of biotechnology, AI chips accelerate the analysis of genomic data, facilitating personalized medicine and drug discovery. The convergence of AI, IoT, and 5G is giving rise to smart environments where interconnected devices collaborate to optimize energy usage, enhance safety, and improve quality of life. Despite the remarkable progress, the journey of AI chips is far from complete. The relentless growth of AI models, exemplified by large language models and generative adversarial networks, continually pushes the boundaries of what hardware must deliver. Emerging paradigms such as spiking neural networks and analog computing promise to further blur the lines between biological and artificial intelligence, demanding new approaches to chip design and fabrication. The quest for general-purpose AI, capable of reasoning and learning across domains, will require hardware that is not only powerful but also adaptable and efficient. Ethical and societal considerations must remain at the forefront of AI chip development. As these chips enable increasingly autonomous systems, questions of accountability, transparency, and human oversight become ever more pressing. Ensuring that AI chips are designed and used in ways that respect privacy, promote fairness, and mitigate unintended consequences is a shared responsibility among engineers, policymakers, and society at large. The creation of inclusive and participatory governance frameworks will be essential to guide the responsible evolution of AI hardware. In conclusion, AI chips represent a cornerstone of contemporary and future computing. Their ability to accelerate complex workloads, enable new applications, and drive efficiency underpins the ongoing AI revolution. By bridging the gap between abstract algorithms and tangible outcomes, AI chips are not only transforming technology, but also reshaping the contours of society, economy, and culture. The continued advancement of these chips will hinge on interdisciplinary collaboration, thoughtful stewardship, and a commitment to harnessing their power for the greater good. As we stand on the threshold of an era defined by intelligent machines, the importance of AI chips in computing cannot be overstated. They are the engines propelling us into a new age of possibility,